Okay, I'm going to start the next topic. The next topic usually it is called the rigid ends. Okay. When we establish the frame elements, usually we talk about that's the center line. Okay, and we have the I of x, A of x, and although we know the I, they are related to the dimensions of the cross sections. Also, the A is the sectional area, which is also related to the sectional area. But when we derive for example, the flexure stiffness or the axial stiffness, we need to consider the moment of inertia, the sectional area, and that's the calculations of the I and the A. So we have a center line. Then we can use these two to calculate the V of x, U of x. Okay, and all the derivations we consider a center line, and also we have the related sectional properties like the moment of inertia, sectional area. But actually, we don't need the real size of the dimensions. Okay, when we derive the flexural stiffness or the axial stiffness, we don't really need the real size of the sections. So we don't know whether the beam element is a rectangular cross sections or the element which is the wide flange, okay, or okay. So the section could be they could have many different shape of the sections. We could have the rectangular cross section, the wide flange, the I-shaped section, the double angle, the cross section. But we don't know all these details. Okay. Also, we don't restrict what kind of the cross section we need. We like to consider. The only thing we required is the users need to know what is the moment of inertia of the cross section and what is the sectional area of the cross section. And after the users calculate these two, then we can input it to the program. So in the program, we consider the center line. And the center line is defined from the node A to node J. Okay. From the node A to the node B, usually we think it is the center line of the element. Okay, we define the center line of the beam element or truss element, whatever. Actually, we define the locations of the center line, and for the center lines, we need to know this is the sectional property. Of course, we still have the Young's modulus, the material properties. For example, the Young's modular, Poisson's ratio, or shear modulus, something like this. But that's the all the all the data the users need to tell the program. The locations of the center line. Also, the related sectional property, especially for the moment of inertia, the sectional area. And the first one is related to the flexure stiffness. The second one is related to the axial stiffness. And sometimes we need to input the shear area, and the shear area is related to the shear stiffness. And after we input all these, actually we don't need to tell the program the shape of the cross section or the detailed dimension of the cross section. We don't need to tell the program. Okay, so that's the what we considered for the frame elements so far. Okay, but let's check the real structure. Actually, we have the dimensions of the element. Okay. So again, not only the center line. Okay, for the real structures, all elements they got the real dimension. All elements they got the real dimensions. For example, that's the column element, that's the beam element, and it is a very common. It is a common cross section you consider. Okay. Okay, so that's the real structures. We have the real size of the elements. Okay, and in the structure model, we consider the center line to the center line. Also, we need to input the moment of inertia and the sectional area. But for the most users, when they consider the elements, usually they will cut a cross section like this one. Okay. If we like to consider the beam element like this one, we will cut a cross section and check. We have the B, we have the H, and then we can calculate the I. Okay, that's the beam sections. But in the real structures, the rectangular cross section, the width is the width B, the height is the H, which is applied only to the column face, Okay. Only from. Okay. So the sectional property we input to the program. Usually we cut the cross section and to check the shape of the sections, and then we can calculate the moment of inertia. Then we can calculate the sectional area. But the calculated results for the moment of inertia and the sectional area, which can be applied only from the column face to the other column face. It is not from the center line to the center line. Okay, remember it is the calculated moment of inertia and the sectional area applied only from column face. Remember, not the intersection of center line to the intersection of the center line. For the beam element input data, we consider from this point to this point. Okay, that's the structural model. That's the intersections of the center lines of the beam and the column. That's the intersection point from the of the right end. That's the intersection point of the beam element and the column line. The length of the element we consider is from this point. That's the point A. That's the point B, and we consider the joint of the elements. The joint of the columns and the beams. Usually we define the nodal points. They are the joints of the elements. So for the left end, it is this point. At the right end, it is this point. This is the length of the element we consider. And if we input the I and the A to the program, but remember the I and the A, they can be applied only face to face, the column face to the column face. But it is not really the calculated I and A, which cannot apply to this part. Okay, so the input I and A so from the column face to the center, to the joint, to the nodal points, that's the part where is the okay, from the column face to the joint, actually the sectional area is not correct. The sectional area, which is not the shape of this one. The cut cross section, which is applied only for the center of the beam element. It is not correct for from the column face to the intersection point of the center line. They say that's the joint. From the joint to the column face, we have different stories. So no matter the moment of inertia or the sectional area, they are totally different from the input data. Okay, so that's if we consider the real size of the structural elements, we will find that the input data cannot be applied for all the sections of this. Okay, then what we can do for the element? Usually we can say that's the joint A, that's the joint B, and that's the element. And we have actually you can say there are three parts of the element. That's the first part. That's the second part. That's the third part. Okay, for the second part, we have the input I and the A. Okay, so usually we require the users to input the second part of the sectional properties, like the moment of inertia or the sectional area. But for the part 1 and part 3, assume the I approach infinity, the A approach infinity. Okay, so that's the assumptions for the part of the element in the real structures. For the part 1 and the part 3, they are the parts start from the joint to the collision phase, and to the right end it starts from the collision phase to the joint. Okay, so for the first and the third part of the element, we will assume the moment of inertia close to infinity, the sectional area close to infinity. Since we have very large cross sections, if you include the part of the columns and the part of the perpendicular beam element, you can say no matter the moment of inertia or the cross-sectional area, they are very large. So in the assumptions, we assume this one. If we assume the I is infinity, so it means the part of the element, it cannot be bent. Okay, so if the I is approached to is close to infinity, if the I is close to infinity, so it means for this part of the center line, it cannot be bent since the moment of inertia is so large. So it means it is not possible we can apply a bending moment and then we can bend it into a curve. It is not true for the end zones. Also, it is applied. It can be applied to the part 3. Also, the axial deformation can be neglected. Okay, since we assume not only the moment of inertia, also we assume the sectional area A, which is also close to infinity. So at these two parts, we can say the center line cannot be bent, or you cannot compress or get any kind of elongation of the end. And for this part, also they are called the rigid end zone. They are called the rigid end zones. Okay, so part 1 and part 3, they are we can say the end zones. They are close to they are the so-called rigid end zones. Okay, I will take a break here and continue it to the next hour.